and welcome back to Calculus 1. Today on the menu, L'Hopital's rule. First, it's not L'Hopital's rule, it's actually Bernoulli's rule. But the reason why it's called L'Hopital's rule is because L'Hopital was the first one to publish the result. So what happened in good old times is that L'Hopital was this rich guy who really loved mathematics, and he was paying Bernoulli to teach him math and send him papers and things because he was generally interested in math. And at that time, there are no books and internet and anything like that. So Bernoulli was sending him all of the works and papers, and this rule was never published by Bernoulli, but it was in one of the papers. And L'Hopital is taking credit for writing the first calculus textbook ever. So he learned a lot of calculus, and he understood all of it, obviously, and he knew it so well to write the first book. And I believe he wasn't aware at all that this rule was never published before. So for the first time, it's seen the public eye in this textbook, and everyone started calling it L'Hopital's rule, but it's actually Bernoulli's rule. But anyway, what does it say? The rule says that if you have indeterminate form in the limit, you can use the derivative to transform that limit into something that it's possibly easier to solve. So the theorem, which we are going to use, known as L'Hopital's rule, says that suppose that f and g are differentiable on the interval and that the denominator is not 0. So suppose that f and g are differentiable on some interval I, and that g of x is not 0, and then g prime of x is not 0. Then, and and this is very important. We have 0 over 0 or infinity over infinity. I'll explain that. It's called indeterminate form. Then the limit of f of x divided by g of x, as this goes to some value a, is equal to the limit x goes to a of f prime of x divided by g prime of x. Now, these are independent derivatives. These are not, this is not a quotient rule. Yes?
What does it say after that?
After that, g of x is different than 0. So not 0. And g prime of x is not 0. So that's equal sign crossed out, which meaning not 0. The first year.
I had a question. Would it always be equal to that? Because sometimes if you get 0 over 0 or infinity over infinity, then take the derivative, then you get.
The mathematical theorem is mathematical theorem, no exceptions. So the answer to that question would be no. Here is the first example of us considering this. I asked you earlier in a semester to memorize this result. And you know that the answer for this was 1 because you memorized it. But now, with this new L'Hopital's rule, you are able to compute this, because when you plug in sine x, sine of 0 is 0 and x is 0, you have 0 over 0. 0 over 0 is the indeterminate form, and since we have 0 over 0, we can use L'Hopital's rule. So usually we put the LH on the equal sign to show that we use L'Hopital's rule. Derivative of sine is cosine x, and derivative of x is 1. So now when you plug in x goes to 0, you get 1 over 1, which is 1. And now you know the answer. The answer for this limit. So let's take a look at more examples. How about limit x goes to 0, square root of 9 plus 3x minus 3 divided by x. We know that to find the limit, the most basic technique ever is to take the number and just plug it in. You should always try that first. And we also know from chapter 2 that if you get 0 in denominator, that method fails, and you have to either do factoring or do some other witchcraft to solve the problem. So in this particular case, well, in any case, you will try to plug in 0 and see if you get a number. If you get a number, you're done. If you don't get a number, then we have to do something. So looking at this problem, you plug in 0, you get square root of 9, which is 3. 3 minus 3 is 0, so we get 0 over 0 again, which is actually good now because we are learning L'Hopital's rule. So L'Hopital's rule says that you are supposed to take derivatives of numerator and denominator independently to see what happens. So denominator, derivative of x is 1. And in the numerator, derivative of negative 3 is 0, so we don't have to worry about it. It's just the square root. And we know how to take that derivative. So this is what we get. And now, if I get rid of the 1 in denominator, we have 3 over 2 times square root of 9 plus 3x. And when you plug in 0 here now, you get a half. How cool is this? You divide 0 by 0, you get a half, huh? Right? Wouldn't that be essentially what happened? 0 divided by 0, half, clearly. Or 1 from the previous example. So when you have indeterminate form 0 over 0, you are to take independent derivatives, numerator and denominator, and then try again. Plug in 0, see if it works. These L'Hopital rules can be linked, chained together. So you can keep taking these derivatives for as long as you have 0 over 0. Now you already see that 3 over 2 times the square root will not give you 0 over 0 because the numerator is already 3. So obviously you cannot apply L'Hopital rule one more time. So let's see. If we can find. And please observe that I said in the definition, it's not just 0 over 0, it is also infinity over infinity as well, right? So if you get 0 over 0 or infinity over infinity, you will be using this rule. Next example, I know how much you love trig and you are getting ready for Calc 2, which is trig driven, right? We are starting in 2 weeks. How about that? Calc 2 in 2.5 weeks from today. Final exam in a week from today. Like it's tomorrow, next week.
So it starts right after?
No, after Thanksgiving, after the whatever the holiday, the Independence Day. There you go. I know it involves aliens.
The other one was pretty good.
What?
in your Independence Day?
Movie?
Yeah.
Absolutely brilliant, amazing. I love it. Yeah.
Bad scores though. Like sci-fi wise.
I don't watch the scores. I make my own scores. Because people are too, I don't even know. I just don't like people. Anyway. What was I talking about? Oh yes, infinity over infinity. So some of the limits will give you infinity over infinity, and here's a trick question because you all love it. Limit as x approaches pi over 2 from the left. And we have 1 plus tangent x divided by secant x. We know we have a vertical asymptote at pi over 2 for tangent. Secant x is 1 over cosine. Cosine has a 0 at pi over 2, which means 1 divided by 0. There's a vertical asymptote for secant as well. So we're definitely now getting infinity over infinity. It is, again, job for L'Hopital's rule. So what we do is we take independent derivatives. Don't forget to write this limit every line until you get to use it up. That's -1 per line. What is the derivative of 1, 0? What's the derivative of tangent? Very good. And what's the derivative of secant? Nice. And now when you cancel one of the secants, you get secant over tangent. Now you have secant over tangent. If you try to plug in these derivatives, if you try to plug in, you will still get infinity over infinity, and you're just going to get stuck in the infinite loop because they will always produce the same derivatives. They will always cancel to the same value. So taking derivative here forever will just alternate secant tangent spaces forever. So what do we do? How about we just transform this into sine and cosine, see if anything cancels, right? So secant is, don't forget the limit, 1 point off every time you miss it. So secant is 1 over cosine x, and this is sine x over cosine x, and look at that, denominators, same, cancel. If you multiply the upper fraction and the lower fraction both by cosine, then the cosines will just cancel, and all you have is the limit of pi over 2 for sine x. What is that? It's pi over 2.
Wait, so you need to take points off in the work?
In the work, for every limit that you don't write, so there's minus 5 right there. -5 points. Well, actually, you can't. This one, this is a statement of the problem. So -4 right there. Because I'm a terrible person. I was brought up that way. I guess we're all born equal and nice, and then it's just, yeah. Yeah. What happened?
No, my teacher did this.
And then, like, 2 dashes or something underneath that.
I am completely lost.
Instead of writing it out like 6 times, can we just write like limit and then like 2 dashes or something to represent x approaching for the steps to the last one?
I'm completely lost. What are you talking?
If we have to write limit over and over and over again,
Yes,
we
yes.
can have a shorthand.
There is no shorthand for this. You can only write it longer if you spell out the word limit, which has more letters than writing LIM. Like LIM is two characters shorter than the full word limit, right? So this is a shorthand.
I'm talking about the expression under limit.
Oh, x goes to pi over 2. Usually it's like x goes to 0 or x goes to 3. So this was one of the examples that has a longer one. Yeah, but there are no math substitutes that I know of that will make that shorter. So do we all understand that there are only two basic forms, 0 over 0 and infinity over infinity? Those are the two where you can use the rule. That's it. Now what we have? We have 0 times infinity. That's going to be the new situation that can arise. Yes. You mean this? Yeah, it's a sigma summation.
Yeah, it's like summation.
Yeah. Yes? When I plug in, the tangent is infinity because there's a vertical asymptote at pi over 2. And the secant also has a vertical asymptote. Your problem has to have a vertical asymptote at that place. You would know that, I hope, right? It's a prerequisite for the course. With a smile, obviously. Thank you. You guys are awesome. So the next order of business is for us to discuss the 0 times infinity. So this is not a basic form. There is no L'Hopital rule for this. But what we have is the algebraic manipulation that will transform the problem into one of the forms. So when we have 0 times infinity case, we use f equals 1 over 1 divided by f. That's f of x, right? So it's a trick that works very well. F of x equals 1 over 1 divided by f of x. All right, perfect. So now, when we have this, let's take a look at an example. So, limit of, well, this is, there's the introductory example is too spicy. So let's take something less spicy. Too spicy. Actually, exercises are worse. Yeah. And it's interesting, what they did is they only have 3 questions for it. Nice. All 8. Yeah, all 8 exercises for 0 times infinity are trig. All of them. Every single one. From 45 to 52.
Wait, really?
Yeah. Well, we'll go solve 2 examples and you will enjoy it, I guess. So here it is, x squared sine of 1 over 4x squared as x goes to infinity. So clearly x squared is the term that will go to infinity, and when you divide 1 by infinity you get 0, and sine of 0 is very good. So we have infinity times 0. So this is where I am going to use the trick, and I am going to say here on the side that x squared is equal to 1 over x squared. So that's how you use the trick. You pick one of the two functions and you use the trick on it to write it as 1 over the function. And now you bring that in the problem. For 1 point you will write limit x goes to infinity. And then what you have is sine of 1 over 4x squared divided by 1 over x squared. So plug in infinity now. If you plug infinity, on top you have sine of 0, which is bueno. And in denominator you have 1 over infinity, which is... So we successfully transformed 0 times infinity into, in this case, 0 over 0. Sometimes it will turn out to be infinity over infinity. If you are not getting 0 over 0 or infinity over infinity, you did something wrong. So we are going to now put the LH and take those independent derivatives. So put the limit first for 1 point. And now we have derivative in the numerator. Derivative of sine is cosine of the same. And now you're supposed to take the chain rule, the derivative of 1 over x squared. So that's going to be negative 1 and then 1 over 4x squared to the negative 2. And then the derivative of the inside is what? 8x. That goes here. Not negative 2 squared. In the denominator.
Wait, wouldn't it be 1 over x to the negative 2? Like the inside is 1 over 4x squared?
Let me do it one more time. Too many things. So this is 1/4, copy 1/4, right? And then you have x to the minus 2, which would be, you drop negative 2 divided by x to the 3, right? And then these guys will cancel. X minus 2 is going to be negative 2 divided by no coffee, x cubed, right? You happy with that?
Why did they cancel again?
4 and 2 cancels. And then it's the 2 left.
Oh,
So now, a limit for a point. What do I have left? I have in the numerator negative 1 over 2x cubed times cosine of 1 over 4x squared divided by negative 2x cubed. And you see that these cubes drop and then negative 2 and negative becomes a positive quarter, you can actually kick that in front of the limit if you want to. It does not impact limit calculation. So all we're left is the cosine of 1 over 4x squared. So the whole thing is 1/4. So how much is 0 times infinity? In this case, it's 1/4. We can make it anything. So algebra. Algebra, 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 algebra. That's all it is. You keep canceling. You really want to practice and you really want to work out the double fraction in algebra. If you have issues with double fraction, make sure you learn it. So you multiply two that are far apart, you multiply two that are close by, you arrange them. You see that I used a trick over here where I multiplied by x cubed, the top and the bottom, and then that cancels off x cubes. There's supposed to be a -1 over here, which for whatever reason OneNote decided to erase. All right. So here's the problem for you to enjoy. I'll give you about 19 seconds. Limit as x goes to pi over 2 negative x minus pi over 2 times tangent x. I don't know why I have these parentheses, we don't need them.
I have a question. So I got 0 times 0, and because that's 0. That's so if I do that thing, that makes that 0 as well, right? Because 1 over 0.
1 over 0 is infinity.
1 over 0 is infinity. Okay, so it's 0 times infinity again. Oh God. I have to do it again. That's what you're telling me.
You flip the wrong function.
Oh, you have to flip this one?
Yep.
How do you know which one to flip?
Yeah, it's called experience. You will know too when you do all the problems.
Right.
Right? It's like, how do you know how to drive a car? Well, I drove it a lot. So, yeah. You have questions? Are you confused?
Yeah, I never done this, but
What?
this is what I have so far. This turns into 0, this turns into infinity, right? No,
Well, that's pi over 2.
yeah, you went to pi over 2 minus pi over 2 is 0. And then,
Yes.
And then you said that there's a vertical asymptote when you put pi over 2 and tan x, such that is infinity.
Yes. Okay. So, you have the... Good.
Okay.
Now, you move...
I made this one flip. I flipped this whole
Good.
thing. Exactly.
Made it into a function.
Like that.
Mm-hmm.
Okay. And then I rearranged it. So I substituted that in.
Mm-hmm.
And then when I plug in infinity, I get infinity over infinity.
But at what point did you take the derivatives?
Do I take it from here? Or like after this? I'm trying to compare to the notes there.
So, wait, hold on. So which one did you...
I'm gonna try to say that I flipped like this function.
Yeah, you'll have to take derivatives.
After this part?
Yeah, as soon as you flip it around.
So before I substitute it back in, I have to make sure the original function.
No, you substitute, right? You substitute and then you take the derivatives.
Okay. Okay. So I'll take the derivative of this. Okay.
But independent, top and bottom, right?
I got infinity times infinity again.
Yeah, it's just that you have to write the fractions so you can actually see what's happening. 1 over x minus pi over 2, and this line is longer, right?
Because 1 over 0 is infinity.
Is
1 over
infinity.
infinity is 0.
Yeah.
So it's 0 times infinity again.
But this will be tangent here, right, when you multiply. So you have infinity
Times tangent 1?
over infinity. Yeah, 1 times tangent is tangent. Divided by...
See.
I know, it's awesome. I love it. I love it. What?
So you plug infinity after you derive it.
Well, to check. And then if you get infinity over infinity or 0 over 0, you are allowed to use the L'Hopital rule. So, let's see how this works. Good. So x minus, well, this is, first we say 0 times infinity. So we have to use our transformation. And when we plug that in, what do we get? We get tangent x divided by 1 over x minus pi over 2. So now when you plug in pi over 2, we have infinity over infinity. Because tangent of pi over 2 is infinity, and 1 divided by 0 is infinity. So we have infinity over infinity, and we use the L'Hopital rule now. Well, that's when you put this one, this is where your derivatives go. As I said, right? You do the transformation, you check if you have infinity over infinity or 0 over 0, that's when you can take the derivatives. So now derivative of tangent is very good, and derivative of Denominator? Excellent. Good talk, good talk. With the negative. So now, if you see that this parenthesis that it's squared is in the denominator of the lower fraction, that's your d. That goes all the way on top with secant, right? So I have secant squared x times -1 times x minus pi over 2 squared. Oops, I lost the point. Depends which country you're in. Sometimes you lose everything.
But like in America, how much we talk?
In America, it's all about fines. So let's have a $5 fine for every limit. Let's have a $3 fine for every minus on the pi over 2.
But if you're rich, you don't have to pay a fine.
I'm super poor, so just like off me.
So that's all we have. All right. So now, what's secant of pi over 2? It's clearly 1, right? Secant is 1 over cosine. Cosine of pi over 2 is 1. 1 divided by 1 is 1. Awesome. Exactly. So we have 1 times -1 times 0 squared. Boom. Hey, here we go.
I don't get how you got the derivative on the sheet that squared x. Is that just simple derivative?
The derivative of 1 over x minus pi over 2. Well, see, when I do these derivatives, this is what happens in my head.
So it becomes negative and it goes down.
This is 1 over x, right? I don't worry about minus pi over 2 because that's not going to trigger a chain rule, right? So in my head, this is just 1 over x. And I know that the derivative of 1 over x is -1 over x squared. So I just park that pi over 2 there, and that's it. Tons of fun. Next form. How much is infinity minus infinity? All right, it could be, but it also could be 3/4. So let's see. I know, it's awesome. See, guys, this section is full of gems. When you go out with your friends, and yeah, someone tells you like, yeah, what do you know, or something like that, or shut up, or just ask them how much is infinity minus infinity, and then lead with the following example.
I feel like I had that debate in kindergarten.
What happened?
I feel like I had this debate in kindergarten. What's infinity minus infinity?
No, that's not, you know. Like, try with someone who really thinks it's smart. You know, you have a friend. Preferably 4.0 in school. It's the best ones. Okay, what's infinity minus infinity? So let's take a look at this situation. Observe what we have. This is some of the, should I say, common sense that goes with this. You have infinity minus infinity, yet the only two forms that you are allowed to work with is 0 divided by 0 or infinity divided by infinity. So how would you go and massage the problem so that you change subtraction into division? Like, what would be the steps that need to be present for that transformation to happen. The only way how you can go from subtraction into division is through factoring, which will first get you into multiplication, but no worries, we know how to change multiplication and division using 1 over 1 over f rule. So we are technically just slapping another step on top of the previous problems. So we had this vanilla state, right, the default state, where you have a problem that is immediately 0 over 0, infinity over infinity. Take the derivatives and you're done, right? And then we, should I say upgraded? We didn't upgrade, we just had the next level up of the problem, which was multiplication problem, which you use the trick to transform into division problem. Now you have subtraction. So subtraction is going to go into multiplication, and then multiplication is going to go into division. So I like to draw this string now that says infinity minus infinity will go into 0 times infinity using factoring, and then this one will go into 0 over 0 or infinity over infinity using 1 over 1 over f trick. So this is like your roadmap. You use factoring to get multiplication, and then you use the transformation there to get your division. Once you have that done, just make sure you don't mess up algebra, you'll be just fine. Now I know it's asking a lot, but let's take a look at the wonderful example. Limit x goes to infinity of x minus the square root of x squared minus 3x. So this is the situation where you have infinity minus infinity. In blue or blue? This one? It says factoring. Yeah. You only have the two F words that we use. It's either foiling or factoring, right? So that's the factoring one. All right, so let's go. What happened? Well, we're not done. We didn't even start the problem yet.
I thought we were supposed to work on it.
Yes, yes, look. So we are going to first try and factor out x squared from the square root, which gives us 1 over 1 minus 3x left as you take out x squared. So this is all algebra now. So as you can see, when you factor out x squared out of x squared, you get 1. And when you factor out x squared out of 3x, you get 3 over x. So now this x squared goes in front of the root, right? You take that out, becomes an x. So now we have x minus x, square root of 1 minus 3 over x. When it goes in front of the root now, right? It's x squared under the root. And then, yeah, all right. And now, finally, we can factor out the x. And we have x times 1 minus the square root. When you plug in infinity, you see how you get infinity times 0 in this case. So we started with infinity minus infinity, and now we are at the situation infinity times 0. All right, so we know that we are supposed to use the rule here to change this one into division. So 1 minus the square root of 1, 3 over x, divided by 1 over x. And now when you test this, it's 0 over 0. Does it make sense? It's just a lot of steps, a lot of algebra. And now when we have 0 over 0, we can finally use the L'Hopital rule, which means we get to differentiate each one. 1 in denominator, negative 1 over x squared. That's the easy one. By the way, these are exactly the problems where I memorized that the derivative of 1 over x is negative 1 over x squared, because this pops up a lot in these problems. So you just memorize that quickly. The derivative of 1 is 0, so we don't have to worry about it, but we have that negative in front of the root. So we do have a negative here. We know that the square root gives you 2 times the square root in denominator, and then its derivative of the parenthesis goes on top, which is negative 3 over x squared. That's the derivative of 3 over x. So the derivative of 1 over x is negative 1 over x squared. The derivative of 3 over x is negative 3 over x squared. It has to be. Just multiply by 3. So now we are going to multiply by x squared, and that will negative x squared, and that will eliminate some of these x squares. So we lose the entire denominator now because we multiplied, and all we have is the numerator, which says negative 3 divided by 2 square root of 1 minus 3 over x. Yes.
Oh, about the step where you went from where you used L'Hopital's rule, where the negative 3 over x squared on the top.
It's a chain rule.
Well, yeah, but could it be positive? I'm not sure. It's negative 3 over x, so it would be negative 3x to the negative 1. And then the negative 1 would come down to make it positive.
I have a negative in, oh, but that negative, yes. There's one more negative there, which would kill this negative here. Okay, yeah, so it's positive 3/2. All right, that's a really good catch. Nice. Look at this. There's a negative here, and then let's say this one, and then you also get a negative because when you do the derivative, right, the derivative of 1 over x is negative 1 over x squared. So there will be a negative because of this, a negative because of x in the denominator, and you also have a negative in front, which is that one. So it's a triple negative sign there. Nice. Good thing I don't have to do this on the exam. I'll mess it up. Wow. I know how much you love these infinity minus infinity. One more, because we can. You're gonna love this one. Tangent minus secant, obviously.
little nuisance.
Mm-hmm.
I've got no idea how to factor that. Yeah, 10x minus secant x.
Yeah, but what do you?
Because you want to get it to, you have to factor, right, to get it to 0 times infinity.
So you have to break it apart somehow.
Yeah, but I don't know like what tan x equals or what secant x equals.
Well, I can tell you that, but you must know those because those are the
Yeah.
prerequisites for the course.
Yeah, but I took the prerequisites sophomore year of high school.
Yeah.
That's the problem.
So I'll tell you what they are, but then you need to know them for Monday. Tangent is sine over cosine, and secant is 1 over cosine. Yeah. Right.
Do you want us to factor out the sign?
You can't factor out the sine
That's why.
because you can't factor out the sine. What's common for both?
They both have sine and they both have cosine.
The hell is the hell is this? That's cotangent.
Okay, so this is cosine. Isn't it cool? I got them done today.
Why is your eye? This freaks me out.
It's like, it's a decoration.
You see that?
My nails. Their eyes.
She had eyes on the, but just. I mean, it's okay to have. Right. Yeah.
Okay. Okay.
Alright.
So then it's cosine over 1. No, 1 over cosine.
That's it.
Then take out cosine.
Hi. I don't understand. How'd you get 0 and infinity? Like, how do you determine that?
You plug in. Pi over 2. Pi over 2 minus pi over 2 is 0.
Okay.
Tangent of pi over 2 is infinity because if you draw the graph, you see that it goes to infinity.
Horizontal.
Vertical. There will be a vertical
Oh,
aspect of
vertical.
that. Yeah.
Oh, okay.
So each problem since the beginning was you plug in and you see what you get.
And then how come here you did, like, what is this? Like, I don't understand this.
Well, I took, this is like the first function and this is the second function. I took the first function, call it f, and wrote it as 1 over 1 over f. And then this is the
same
main,
thing for this?
and yeah, well, no, I didn't do the same thing. What I need here is this line to be much longer because that's the main division line. It's 1 divided and both of these are in denominator. So now you have this times this fraction, tangent multiplies the one on the top, and that's why it's tangent over. So this is your main division line. It's good here, it's longer. So you have tangent divided by these guys. It's algebra.
And this one, it's the derivatives, right?
Yes, then we'll do L'Hopital rule, which is derivatives of each. Independent. It's not quotient. It's, yeah.
Oh, okay.
It's not. Just regular derivatives, 2 independent derivatives. Fair?
Yep.
No, there was like another portion of like that was hard too. Like me and my
So tangent would be sine x over cosine x, and the secant is 1 over cosine x. So I'm hoping that we should be able to factor out 1 over cosine x, right? Let's see if that helps. It might not. So 1 over cosine x, and then we are left with sine minus 1. Now, when you plug in pi over 2, yay, infinity and 0. Nice. Nice. So now we have infinity times 0. We know the trick that we have to use, right? And you can flip either one of these. Now this is secant actually. The first one is a secant. So you can flip the secant if you want, or you can flip the parenthesis. It doesn't matter which one you use. You can trick. So limit x goes to pi over 2 the minus, and we can say sine x minus 1 divided by 1 over, and then this should be 1 over cosine x over here. Now this is way too many of these guys, so I'm just going to say secant over here. It's much easier.
Can't you just write that as just cosine x with no name?
Mm-hmm. Well, let's do some steps. So now the 1 over secant is the cosine. Cosine of pi over 2 is 1, sine is 0, sine of pi over 2 is 1, so 1 minus 1 over 1, that's 0. So for these guys, we immediately do L'Hopital's rule. For this one, we transform into 0 over 0 or infinity over infinity using the trick 1 over f. For infinity minus infinity, as I said, we are going to first factor, and that will get us into 0 times infinity, and then 1 over f. That gives us 0 over 0 or infinity over infinity. And then you do L'Hopital rule. So we covered 4 of these cases now, right? How many are left? 3. But they all solve the same way, all 3. So all 3 go as a group on a pile, and that is 1 to infinity, 0 to 0, and infinity to 0. How much is 1 to infinity? You would say, oh, that's just 1 times 1 times 1 times 1 times 1. And I say it could be e cubed. Could be anything. This is the amazing thing about calculus. That you really don't know until there's intuition, but frequently intuition can be wrong, and you'll learn that well in Calc 2, where you know, you'll say, I will ask you, actually, those of you taking Calc 2 in 2 weeks, I will ask you to retire common sense and intuition for an entire chapter, actually, and just learn rather than try to sense things. So here I have these 3 forms, and all of these forms will utilize ln, logs. So, rules for 1 to infinity, 0 raised to 0, and infinity raised to 0. Use ln natural log. So what's happening here? Let's start with the most basic example. Limit x raised to the 2x, and x approaches 0 plus. So what am I going to do here? I am going to set this equal to y, leave some space, and I need that space to ln both sides. So now what happens is I have ln y is equal to, now ln can go inside the limit, there are theorems in analysis which help with this if the function is increasing and so on. There's a lot of cool things. So they can swap places, ln goes in. And now we know the rule, hopefully, from pre-calc1 for ln's, that ln x to the p is p ln x, which means that this 2x can jump in front of ln. And now when you try this x goes to 0, you have 0 times infinity. You know what you're supposed to do. It's ln x divided by 1 over 2x, which gives us infinity over infinity. We can finally do the L'Hopital's rule now. So on the left hand side we have ln y. On the right hand side we take derivatives. That's 1 over x for the numerator and 1 over 2 negative x squared. There we go. Multiply by 2x squared, and we have ln y is equal to, we don't need L'Hopital now. We already did the derivative. We're just simplifying. We have 2x, negative 2x. That's all that's left, right? And when you plug in 0, it's 0. So what you have is that ln y is equal to 0. E both sides. And you get y equals 1. But you know that y was defined as your problem. If you look at this line, ignore the red, you see that y is the entire limit from before. So we've shown when you plug in, instead of y, you plug in the limit x goes to 0 plus of x to the 2x is equal to 1. And that's the answer. So we ln both sides. I don't see too many smiles. No? There's one. I can get the fake ones anytime. There you go.
Play dirty. It's not fair.
What happened?
Play dirty. It's not fair.
So it's called dirty. All right, one more. This is problem 66. Limit. They have z values x's because z looks like 2's and then you get confused. So limit as x goes to infinity of 1 plus 10 over z squared over x squared raised to x squared. So previous example was 0 to 0. Which one is this one? One to infinity. Good. Just do it.
E.
Did you roll the where's your Y and stuff?
Pardon? There, but I just like was a bum about writing. But well, this was because I tried doing like the first term as like x squared as the 1 over f, and I didn't like it, so I did the other one.
But you have two ones. You need to only have one.
Why? I thought it was 1 over f.
Yeah, but one is multiplied into the top.
Well, but I didn't even use that. I used this one. X squared over 1 over 1 over. 1
You
plus.
have extra over here. One is extra because that multiplies. This one always multiplies the expression that already is on the top. You're multiplying two fractions.
So it's just 1 over that?
Mm-hmm. And
So does that change it 1 over?
yeah, but where did you take the derivatives?
You know what? I didn't.
You didn't take the derivatives. That's why.
It looked weird.
So many steps.
Y equals, well, it just, follow the flow algebra. That's all it is. So we have ln y is equal to the limit x goes to infinity of ln of 1 plus 10 over x squared to the x squared. Now, if you already know, you can put the x squared in this step, so you don't have to write a million times, but we're learning, so let's do each one. There we go. So now we have infinity times 0. Because 10 over infinity is 0. 1 plus 0 is 1. ln of 1 is 0. So you have infinity times 0. So we're going to use the trick transformation. We have ln of 1 plus 10 over x squared divided by 1 over x squared. So that 1 on top is right here, and we don't have to write it. So when you have 1 over f, that 1 is this one. That multiplies the function that will stay in the numerator. So now we have 0 over 0, and we can use L'Hopital's rule. So I said limit up there should say ln. There we go. So for the derivative for the numerator is going to be derivative, right? So we have copy the function as is in denominator and put its derivative on top. Derivative of this is going to be 10 times negative 2 x to the negative 3. So really small because such is life, I guess. And then we have x squared here, and then the derivative x to the minus 2, so that's going to be negative 2 over x cubed. There we go. Great.
Hey, where's the 1 over x squared thing again? It's like back steps when you like do the 1 over 1
This?
over x. No. When you do the 1 over f.
Oh, okay. This.
Yeah, just for the x squared.
So I'm writing x squared as 1 over x squared. So this 1 is in line with x squared, which is in line with this, and multiplies it. And then these guys are just these.
Okay. Thank you.
Bueno? All right, so I'm going to write this much larger now because we have to do a lot of algebra to clear this up. I have negative 20 over x cubed divided by 1 plus 10 over x squared. And the main division line here divided by negative 2 x cubed. So I'm going to multiply by negative x cubed first, and that will cancel the negative and the x cubed and the negative and the x cubed. Yeah, I was doing this yesterday and then I had to restart and reboot, and it did the update, and then it was fine, and it looks like they pushed a new update. I think that's how Microsoft now forces us to do updates. Anytime there is an update available, the software starts crashing. So, and the only two options that I have are shut down an update or restart an update. It's not there yet.
Almost like a Unix-based OS would be better.
Do what?
It's like a Unix-based OS would be better.
Well, Unix, well, no, the Linux is the best operating system now on the market, but it's just not compatible with a lot of stuff that we need yet. And it's also free, which is the most amazing. All right, so all of these die.
I'm saying Mac OS X is Unix-based too, isn't it? Mac OS X is Unix-based.
Yeah, but as a platform is useless for enterprise stuff. Like a lot of software doesn't work on it because
Yeah.
it's not a serious platform. So that's why. Yeah.
Can you run any of those programs on the Surface?
Which one?
Like engineering programs?
All of it.
Really?
Yep. If it runs video games, it runs everything. Because video games are the most stressful for any system. So anything else would be less, like Photoshop and AutoCAD and everything else. It's just going to be less demanding. If it runs video games, it runs everything. And Surface runs video games, so I actually have the other one with stuff installed. Alright, so what do we have here? This is divided by 2, so that's just going to be 10 divided by 1 plus 10 over x squared. When you plug in infinity, the whole thing becomes 10. And we have ln y is 10. We e both sides. And we have y is equal to e to the 10. But this was the problem. So limit x goes to infinity of whatever the problem was. 1 plus 10 over x squared raised to the x squared is equal to e to the 10. Done.
Can you scroll?
How do you know if it's come? Oh,
Hey, Dad. Can we vote on the exam now? Before we put it in? Are you guys gonna Tuesday?
All right, let's just do one more thing and then we can do that.
Alright.
So now you've seen all of these limits, and there is one situation where we can use the theorem of the what we call growth rate of functions, where we can quickly decide whether the limit is 0 or infinity, and that is only for case when x goes to infinity. So when you have a case x goes to infinity, you can look at the functions and their growth rate will tell you what the answers are. So on this side we'll have slow functions, and on this side we'll have fast functions, and this will all be repeated later and expanded in Calculus 2 to include even more stuff when we move into the discrete realm. So ln raised to any power of x is one of the sluggiest functions out there. And then you have polynomials which rise faster, and then all of that will be smaller than when you multiply polynomial and ln together. So on their own, ln are the slowest, and then you have polynomials being faster, and then obviously if you multiply the two together you get faster still. Now that's smaller than when you multiply two polynomials together. So we can write that as p plus s. So that's like x to the 4th times x to the 8th, right? That's faster than previous one. And all of that is smaller than x to the x. So x to the x is considered to be like a boss in this situation. So this is known as the growth rate of functions. And the way you use this, the way we use this is if you have limit x goes to infinity of slow over fast. I put these quotation marks because trying to get the message across. You get 0. And if you have limit x goes to infinity of fast over slow, you get infinity. So think about this is, let's say you have ln x divided by x to the 5. So that's going to be 0 because x to the 5 is polynomial which is faster than ln x. Now when I say growth rate and when I say fast and slow, what do I mean by that? Well, it's how fast the values, the y values grow as the function progresses. And I'll just give you a few examples here. I don't want to do too many of these. Let's say this is x, and then you have 2x, and you have x squared, and you have 2 to the x. And then finally x to the x. So if you just compute this for 1, 2, 3, 4, 5, and 6, it will immediately become clear what it means by growth rate and why some functions are faster than others. So over here you have 2, 4, 6, 8, 10, and then 12. So you see that 2x is growing faster than the other one, as all values are larger. And then x squared is 1, 4, 9, 16, 25, and 36. You see that this grows faster than any of the previous ones. Now 2 to the x, well, 1 to the 2 is 2, 2 squared is 4, and then 2 cubed is 8, and then 16, and then 32, and then 64. Remember how they say, oh, grows exponentially. If you look at the linear growth, which is your 2x, and you look at the exponential growth is really large over there. You get 64 on the 6. But x to the x is the boss of all of these. X to the x is at the end over here, means fastest. 1 to the 1 is 1, and then 2 squared is 4, and then 3 cubed is 27. Look at that. And then 4 to the 4 is 256. You see what's happening here? This one is absolutely wrecking anything else. And then you have 5 to the 5. 5 to the 5 is going to be 625 times 25, which is a lot. And this is even more. We're talking tens of thousands on number 6 already. So without us pulling the calculator and so on. So when you see x to the x in the numerator, most likely you will have probably infinity as the answer. If you see it in the denominator, most likely you will have 0. Now that's not a rule, that's just, I said most likely, but you could have these guys float around, and then you just have to be a little bit careful with these things. That ends this section. I will let's go for the break and vote on the test and all of that stuff, and then we are going to move through the rest of the chapter. So by stream, right? We'll restart this soon.